So in the last class we have discussed about what is delivery, okay, what is direct delivery, indirect delivery, and then we have discussed about what is forwarding. And in the forwarding method we looked after next hop method and a route method, and then we have discussed about the network specific method, host specific method, and then we have discussed about default method. Okay, these are all about the forwarding techniques. And then later we discussed about what are the contents of the routing table, right? So how a routing table will be constructed for a particular router, okay, and then how a router is going to forward the packets to appropriate network only basing upon the mask. So it is going to search for the longest mask. And then we have discussed about what is a routing table and what is a static routing table and dynamic routing table. And then we have discussed about what are the different fields in a routing table. That is, the fields in the routing table are mask, network address, next hop address, interface, flags, reference count, and use. So these are all the different things that are different concepts which we have discussed in the previous class. Okay, so now we are going to discuss about unicast routing protocols. So here we are going to discuss about the concept of routing protocols. Okay, so why we are calling it as unicast routing protocols means, so we discussed already about unicast routing, that is we'll be sending the information or packets from one source to one destination, right? So now, a routing table can be either static or dynamic. This we have discussed in our previous class, right? So it could be either static or it could be dynamic. So what is the meaning of static? Static means the entries are done manually, isn't it? That is, the administrator has to change the entries manually, or he has to update the entries manually. Then what about the dynamic table? So in the dynamic table, the entries are updated automatically whenever there is a change in the internet, isn't it? So whatever change is happening and whenever the change is happening, automatically the updations will take place. So for these updations to take place dynamically, we require routing protocols. Okay, so what is a protocol? In the first unit itself we discussed about protocol is a set of rules, right? So routing protocol means which is a combination of rules and procedures which allows the routers in the internet to inform every other router about the changes in the internet. That is, there could be one router here and there could be another router here and there could be another router here. This router has to inform this router about the change in the internet, and this router has to inform this router about the change in the internet. So for this reason, for communicating of these changes in the internet, we need a protocol which is nothing but we are going to call it as routing protocol. Okay, so this is what we are going to call it as routing protocol. Next, so actually why the routing protocols have been created? Act to have the dynamic routing tables, just now we discussed it. So the dynamic routing tables, that is the routing tables must be modified or updated automatically with respect to the change in the network. So for this reason only, that is due to the demand for the dynamic routing tables only, the routing protocols have been created. So now what does these routing protocols include? They include the procedure for combining the information which is received from the other router. Okay, so there is one router here, the one another router, this is another router. So whenever this router sends some information to this router, now what does this router do? It combines the information received from this router along with the information at this particular router, and the similar thing happens with this particular router also. So this is how these routers which are connected in the network will communicate with each other, and they come to know about what's happening in the network, and they come to know about how to update their entries in the routing tables. Okay, that we'll be seeing shortly. Now coming to optimization. So what is optimization? Optimization in general terms, which is nothing but it depends upon the different context. If you are writing examination, what is your optimization criteria? Your optimization criteria is to get good marks, right? So if you are going from one place to another place, what is your optimization criteria? Your optimization criteria is to go in short span of time. isn't it? So like that, for each and every application we have different optimization criteria, right? So in routing also we have optimization criteria. Actually the router receives a packet from the network, isn't it? So whenever we have two routers here, let us say this is router 1 and this is router 2. Now this router 2 receives the packet from another network, isn't it? Okay, so the packet will be passing through this particular network. Okay, so this is a network, and for this network routers have been connected, right? So the packet passes from this router to this network, and from this network to again to the router, isn't it? So this actually happens in our network. So if you observe, the router is attached to several networks. Right from the starting of our discussion we are discussing this. There is a router is usually attached to several networks. So now the question is, when a particular router receives a packet, to which network should this router pass the packet? Okay, so this router is receiving the information, and from this router to which network it has to pass the information. So this is our question. So to which network it has to pass, through which route it has to pass this particular packet, so as to do some optimization. So this decision, that is the decision of the packet, the decision of to which network a packet has to be sent, okay, is done on the optimization criteria. Okay, so now the router, from among the available multiple paths, now the router will choose the optimum pathway, that is through which it has to send that particular packet. Okay, so now what is the definition of the term optimum? So we have to define what is an optimum pathway. Okay, so actually to define the optimization criteria for the routes in our network, we have different types of approaches. So actually the first kind of approach is we assign a cost for a packet passing through a network. So this is our network, right? So this is our network, right? So in this network there are different routers. Okay, so we assign cost for a packet which is passing through a particular network. So this could be one network, and here we may have combination of routers and hosts, and there could be another network also. That is from one network to another network the packet is being passed. Okay, so when it is passing through a network or within the network or from network to networks, we are going to assign some metrics. Okay, that is the cost incurred, okay, to transfer a packet from one place to another place. Okay, so this we are going to call it as a metric. Okay, so this cost is what we are going to call it as a metric. Actually there could be many metrics available here. Okay, now how we are going to assign these metrics? So these metrics are assigned depending upon the type of the protocol. So what type of protocol we are using, so depending upon the which type of protocol we are using, the metric assigned is also dependent. Okay, there are different types of routing protocols. If you take for example the routing information protocol, commonly called as RIP. Okay, so this routing information protocol, it treats all the networks as equal. So when it treats all the networks as equal, that is there is no differentiation between different networks, then what could be the metric here? Now the cost of passing a particular packet through the network is same. So when it is considering all the networks as equal, so it considers the metric to be same, that is simply one hop count. That is, here say, let us say this is one hop, and this is another hop, and this is another hop. Okay, so if the packet transfers through from this hop to this hop and from this hop to this hop, so here the count is 2. Okay, so if a packet is going to pass through 10 networks to reach its destination, then the total cost is 10 hop counts. Okay, so this could be one network, and this could be another network, and this could be another network, and this could be another network. So if the packet is passing through n number of networks, then the hop count is n. So if the packet is passing through 10 networks to reach the destination, then the total cost is 10 hop count. So this is how the metric is going to be done in the routing information protocol. Now, coming to the other kind of protocol, which is nothing but OSPF. OSPF is nothing but Open Shortest Path First. So this is another kind of protocol. See, if you see in the previous protocol, that is in the RIP protocol, now we consider the metric as hop count. But now coming to the OSPF protocol, here this protocol uh, takes the metrics basing upon the type of service. Okay, what type of service we are using. So that here the metric is in such a way that if we are going to use one type of service, then that is there, then there will be one kind of metric. If you are going to use another type of service, then there will be another kind of metric. That is, here it is not going to treat all the networks as equal. Okay, so now it will be having obviously different metrics, right? Let us say, for example, if the type of service we are desiring is maximum throughput, that is, if we want our network to have maximum throughput, then obviously the satellite link will be having a lower metric when compared to the fiber optic line. But if our type of service we require is minimum delay, that is, our network should contain minimum delay, then obviously the fiber optic line, that is the fiber optic communication network, will have a lower metric when compared to the satellite link, isn't it? So in this manner, basing upon the type of service required, the metric also varies. Okay. So how now the routers will choose the best route? As we already discussed, the routers will choose the best route basing upon the routing tables. Okay. So here the OSPF protocol allows each router to have different routing tables based on the required type of service, because according to one type of service, one metric is okay. For another type of service, it requires another metric. So depending upon the type of service, it allows each router to have different types of routing tables also. So anyway, we will be going to discuss about what is OSPF and so on, how that protocol is going to work in the forthcoming sessions. Now, so there could be another protocol also. So some other protocols may define the metrics in completely different way. So if you see, for example, another protocol called BGP, which is nothing but border gateway protocol. So if here the criteria is policy. Okay, so previously for OSPF, the criteria is type of service, right? For now, coming to the border gateway protocol, here the metric or the criteria is policy. So this policy is set by the administrator. Okay, so now this policy will tell, or this policy will define which path should be chosen. Okay, so depending upon the protocol, the metric is also going to change. Now, coming to the next concept of intra and inter-domain routing. So actually, the internet, the present internet, is a combination of large number of networks. So a single routing protocol cannot handle the task of updating the routing tables for all the routers, right? If there are only two or three, or let us say some 10 or 20 routers, and then we'll be having 10 or 20 routing tables, then it is a normal task. But here the internet contains billions, millions and billions of devices. Okay, so updating all these things manually, it's not completely a possible task, right? So here one routing protocol is not sufficient to handle this task of updating the routing tables, right? So for this reason, what actually has been done is the internet is now divided into autonomous systems. Okay, so we'll see what are autonomous systems. Okay, so for because the internet is large, we have divided it into autonomous systems. So if you see, actually our college is an autonomous college. So why we got autonomous status? Actually, so we are under some big university. If so, that big university cannot manage all the colleges under that university. Okay, so when a particular college is maintaining some standards, then it will be given autonomous status. Okay, so like that, in order to manage the 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 different engineering colleges under a particular big university, then they are going to grant the autonomous systems. Of course, an engineering college could be an autonomous college, but it works under the guidelines of the university only, isn't it? So in this way, an autonomous system is a group of networks and routers, and it works under the authority of a single administration. Okay, so if you say that it is an autonomous system, so this autonomous system consists of a group of routers and networks, and it works under a single administration. Okay, now what we say, routing, if it happens within or inside an autonomous system, then it is called as intra-domain. Intra means same. Okay, so if the routing happens within the autonomous system, then it is referred to as intra-domain routing. And if the routing happens between the autonomous systems, then it is referred to as inter-domain routing. Okay, so if you take two autonomous systems, every autonomous system can choose one or more intra-domain routing protocols, but we have only one interdomain routing protocol to handle the routing between autonomous systems. Okay, so if you see, this is our autonomous system representation. So this is our autonomous system 1, it is our autonomous system 2, and this is our autonomous system 3, and this is our autonomous system 4. Okay, so within a particular autonomous system, that is within this particular autonomous system, we can have any number of intra-domain routing protocols, but between, between these two we have only one inter-domain routing protocol, and between these two we have only one, and between these two we have only one inter-domain routing protocol. But within a particular autonomous system, we can have n number of, or we can have more than one number of intra-domain routing protocols. Okay, so if you see, this is our autonomous system. So it consists of nodes and it consists of routers. So it consists of different types of networks also here. Okay, so this is what we are going to call it as an autonomous system. So actually there are different types of intra-domain and inter-domain routing protocols are in use currently. So we are going to discuss about only the intra-domain routing protocols and one inter-domain routing protocol also. So if you see here, there are two major intra-domain routing protocols. The first one is distance vector routing protocol, and the second one is link state routing protocol. These two are examples of intra-domain routing protocols. And coming to inter-domain routing protocol, we are going to discuss about the path vector routing protocol. Okay, so intra-domain is distance vector routing and link state routing, and inter-domain is path vector. Okay, so now if you see, in this figure you can see the different types of routing protocols. So the routing protocols have been divided into intra-domain routing protocols and inter-domain routing protocols. So if you see, in the intra-domain we have distance vector routing protocol and link state routing protocol, and in inter-domain we have path vector routing protocol. Actually this RIP, which we have discussed about just now, that is routing information protocol. This RIP is an implementation of distance vector routing protocol, and this OSPF is an implementation of link state routing protocol, and this BGP, border gateway protocol, is an implementation of path vector routing protocol. So these two are the intra-domain routing protocols, and this path vector is the inter-domain routing protocol. So now first of all we'll be discussing about the first protocol, which is nothing but the distance vector routing protocol. So which is the first intra-domain routing protocol in our routing protocols. Okay, let us now discuss about the distance vector routing protocol. So if you divide this particular name of this algorithm, distance vector routing protocol or some algorithm, so here it just specifies that the first thing is distance, the second thing is vector, and the third one is routing. So distance means the main metric or the main consideration here for this protocol is distance between the nodes. Okay, and then vector, that is it is going to maintain the vector of all the distances. So basing upon these two information, it is going to do the routing. Okay, so let us now see what is distance vector routing protocol and how this distance vector routing protocol is going to work, and so on. Okay, so now coming to the distance vector routing protocol, the least cost route between any two nodes is the minimum distance. Of course, this is the universal fact, right? So if you consider two nodes, right? If you consider two nodes, this is node 1 and this is node 2. Okay, it may have multiple routes. This could be one route, this could be one route, and so on. But we are going to consider a least cost route only as the minimum distance route, right? So in this protocol, so as the name implies, distance vector routing, each node maintains a vector. That is, each node maintains a table of minimum distances to every node. So we'll be seeing shortly, we'll be having different nodes, and each and every node is going to maintain a vector, or it is going to maintain a table of minimum distance. That is, from this node to the next node, what will be the minimum distance? Okay, that information each and every node is going to maintain. Okay, also the table at each and every node, also it guides the packets. Okay, so through which node it has to reach. Okay, so here we have nodes and we have lines. Okay, so nodes can be considered as cities in a particular area, and lines can be considered as the roads which are connecting them. Okay, so what this table is going to do, it is going to guide these nodes through which hop, that is the next hop, through which next hop the packet has to be routed. Okay, so if you see, if you have a particular plan, okay, if a tourist is going to visit a particular place, okay, that or if you go for Google, it is going to show you the minimum distance or the shortest distance between source to destination. So here also the table is going to show, but if we consider ourselves for a packet as a tourist, it is going to show the minimum distance between these cities, that are the minimum distance between two nodes. Okay, so if you see here, this is the example which you can see on the screen. So this is showing the system of 5 nodes with their corresponding routing tables. So let us consider an example for now the node A. So if you consider the node A, from node A to node A, that is how a packet can reach from node A to node A with zero cost, right? So we have node A to node A. Because this is the A's routing table. So A to A, the cost is zero. Okay, obviously the next stop is nothing. And from A to B, so from A to B, if you see here, what will be the cost? The cost is 5. So A to B, it is 5. There is no next stop because A is directly connected, right? Next. And from A to C, it is 2. Next. From A to D, it is 3. And from A to E, so can A directly reach to E? No, right? Because the node C is in between A and E, right? So from A to E, it has to go from A to C first of all, and then from A to C, and then from C to E. So 2 plus 4. So 2 plus 4 is obviously 6. But the next hop is here C, because A cannot directly reach to E, it has to go through C. Okay, so this is how we are going to represent the table, that is the vector distance vector table. This is a vector of all the distances. Okay, now so for similarly for B also, so B to A it is 5, and B to B 0, B to C it is 4. Okay, see, B to C it is 4, and B to D, B to D means here some B to D. So what will be the next stop? It has to from go from B to A and from A to D. So that is the reason we have next hop A, and B to E directly with 3 units, right? So this is how we are going to maintain the distance vector routing tables in our protocol. Okay, so I hope this is clear how we are going to put these values for each and every node in the given network. Okay, now next. So if you consider for a particular node A stable, okay, so we can reach any node from this node, right? So from node A we can reach any node, that is from node A we can reach node B, we can reach node C, we can reach node D, and we can reach node E also. Okay, but in between from node A to node E, of course you have to go via node C. Okay, so this is how each and every table is going to be given some values. Okay, so if you see, the least cost to reach a node E is 6. From A to E, the least cost is 6. So, but this route actually passes through C, right? So for this reason, we kept this next column here as C. For all other things also, it is like that only. Okay. Now, let us now see how actually the distance vector routing protocol is going to work. The first thing is initialization of these tables, initialization of these distance vector routing tables. So if you observe here, the tables which we have here are stable. Okay, stable means we assume that the network has reached a stable condition. Okay, actually the network initially will not be in a stable condition. Actually after some time only the network will be getting a stable condition. Okay, so let us assume that if the network has achieved, or the network has come to know the details of every other node, so that we assume that the complete network is stable now. So if the complete network is stable now, what happens? Every node knows how to reach to every other node, and what is the cost to reach to every other node. Okay, so if you see here, if the network, do remember, very important, if the network is stable, after getting stable only, every node comes to know what is the distance between that node to another node, and what is the distance between that node to some another node, and what is the cost incurred for reaching to that particular place. But initially it is not the case, right? So when we initially started deploying the algorithm, this is not the case actually. So then initially every node must come to know what is the distance between that node to another node, and what is the cost incurred between that node to another node. Okay, so for this what we are going to do, So initially what actually happens is every node knows only the distance between itself and its immediate neighbor. That is, if you see here, only if you, let us say, consider E. So if you consider E, this E initially when it is deployed, it knows only the distance between this E and its immediate neighbors. What are E's immediate neighbors? C and B. That's it. D is not an immediate neighbor to E, and A is not an immediate neighbor to E. Only E knows the distance about E to C and E to D. That is the only thing, because these are only the immediate neighbors. Okay. And so for this moment, what we are going to assume that each node will send a message to the immediate neighbor, and it finds the distance between itself and these immediate neighbors. That is, let us say E will send the message to C telling that what is the distance between you and me, and E will send the message to B asking that what is the distance between you and me, so that appropriately they can identify the distance between the immediate neighbors. Okay. Now, so if you see the initialization, how it has been happened. Okay, so don't get confused. When after this diagram is about the network whenever it reaches the stable state, but initially the tables of each and every router will look like this. If you see again, let us now consider. So the initial tables for each node will look like this. So for A table, A to A 0, A to B, of course it has sent the message because B is the neighbor of A, so there is no problem, it is 5. And A to C, it is 2, no problem. A to D, it is also immediate neighbor, no problem. But from A to E, is E an immediate neighbor to A? No. For this is the reason here we say that we mark this particular cost to be infinite, that is unreachable. That is, currently A cannot reach to E. So if it want to reach to E, obviously it has to reach via C. But initially what entries we are maintaining? We are only maintaining the entries through which a particular node can reach the other node directly without any intermediate node. And if you take example for B, so B is directly connected to A, and B is directly connected to B, and B is directly connected to C, and B is not connected to D. Okay, and B is connected to E. So because B is not directly connected to D, we do not know the distance between D and B, right? For this reason we mark that distance as infinity. So for everything, so from E to A we cannot directly connect, so infinity. From E to D also we cannot directly connect, so it is infinity. So like that, this is how the initialization of tables happens in the distance vector routing protocol. Now, sharing. So now how these routers are getting the information? Basing upon sharing the information only. So when a particular router shares the information to the other router, only then the other router comes to know the distance between this particular router and the other router, right? So now the main idea or the whole idea of this distance vector routing protocol comes from the sharing of information. Okay, so actually just now we discussed A do not directly know about node E. Okay, but how can node A come to know about node E? C knows how to reach node E, right? So when C knows how to reach node E, and when A knows how to reach node C, then obviously A can know how to reach node E, right? That is, if A can reach node C and if C can reach node E, then obviously A can also reach node E with the help of whom? C. Okay, so this is how they are going to take the sharing, or they are going to share the information from one node to another node, so that they can reach to the other destinations, or so to the other neighbors which they are not directly connected to. Okay, so and also here if you see node C cannot directly reach to node D, but node A can directly reach to node D. So now what C will do? Now C will ask A, okay, and A will ask D. Okay, so now C will now get the information via A, and it can reach to D. Okay, so this is how each and every node or each and every router is going to help each other. They remove from get the help from the immediate neighbors, and they can tell this information to the immediate neighbors so that those immediate neighbors can reach the other destinations. Okay, now, but here we have only one problem by doing this. Okay, so when we are telling that these tables are being shared from one neighbor to the other neighbor, the question is how much of the table must be shared with each neighbor. So what does the actual table contain? It contains the two information, the actual cost information and the next node information. So among these three columns, how many columns or how much information must be shared to the other neighbor? So this is our question. So the answer for this is that actually the neighbor is not aware of the a node is not aware of the neighbor's table, right? Initially, let us say if you take node A, this is not aware about the neighbor's table. Only when B shares its table, then only A comes to know about the B's table. So the solution, the best solution is that each node send its entire table to the neighbor and it allow the neighbor to decide which part to use and which part not to use, isn't it? So the answer is the neighbor. Let us say if the node B send its complete table to node A. Now it is now the decision of node A to use which of these information received by the node B. Okay, I hope it is clear. Okay, let us take another example. Now node E is sending its table to node C. Okay, now it is the decision of node C which columns to retain and which columns to discard. Okay, so if you see the third column, that is the next stop or next hop column is not useful for the neighbor. Okay. So actually when node E send the information to this particular node C, this next hop or next node column is not useful for this node C. Only it requires the information of these first two columns. Okay. For this reason, the third column is discarded. Only these first two values will be used. So what actually happens now? So as the a neighbor is going to receive, that is the when C receives the table from node E. Now we said that this last column is of no use. So what will be the last column value then? So the last column value is replaced with the sender name. Okay. So who is the sender here? Node E is the sender to node C. So this last column value is replaced with E. That is all entries will be replaced with E because node E is the sender of this particular routing table. Okay. Next. So if any of the rows can be used, then the next node is the sender of the table. So if you see, if because node E is sending the information to node C, right? So if node C can use any of these values, then obviously the next node will be now node E only. Okay. So if we see the example, then it will be easy for us. Okay. So here sharing is only about the first two columns. So finally what we can say in distance vector routing, each node shares its routing table with its immediate neighbors only, and that too only periodically. When will be the routing tables be shared? Only when there is a change in the network. Okay. And sometimes periodically also these values, I mean these routing tables must be shared. So in distance vector routing, every node shares its routing tables with every other node periodically and only when there is a change in the network. Now coming to updating. Now whenever these nodes are sharing their tables, obviously these nodes has to update their tables basing upon some criteria, right? So when a node is going to receive a two column table from its neighbor, it has to update its routing table, right? So now let us now see how this updating takes place. So actually updating in this distance vector routing protocol takes in three steps. Let us now see each and every step in detail. Okay, let us now consider about the first step. So the receiving node needs to add the cost between itself and the sending node to each value in the second column. Okay, don't worry if you do not understand this. Okay, it is very simple. Okay, if you see, let us say if node C tells that its distance to a particular destination, let us say some D is X. Okay, and the distance between node A to node C, if it is Y, then what will be the distance between node A and node D? It is X plus Y. Okay, so this is the meaning of this statement. Okay, so the receiving node. So what is the receiving node? Let us say if the receiving node is A. Okay, the receiving node needs to add the cost between itself. Okay, cost between itself and the sending node. So who is the sending node? Let us say C. Okay, so it has to add the cost between itself and the sending node to each value in the second column. So this is the second column. Let us see. I'll tell you the example. Okay, but for now you understand this one. Okay, if node C and node D distance is X and node A and node C distance is Y, then what it has to add? It has to add this value and this value, so that if it wants to reach from node A to node D. Okay, so now let us see how this happens here. So if you see here, the receiving node, or who is the receiving node here? Let us say we assume the receiving node is A. Okay, now the C is going to send its values to A. Okay, so let us now check how A is going to update its routing table when it receives the information from node C. Okay, so now about the second point. Now the receiving node needs to add the name of the sending node. Okay, if we consider the receiving node is node A and the sending node is node C. And what is the second point telling? The receiving node needs to add the name of the sending node. So what is the name of the sending node? The sending node here is C, the receiving node here is A. So the receiving node needs to add the name of the sending node to each row as the third column. Okay, so actually every router is going to have three columns, right? So here the next hop value is actually initially dashes, right? That is, there is no next hop, and here there is nothing here because it cannot reach E, right? During the initialization of tables, that is the reason we do not have any entry here. But now what it is saying, the receiving node needs to add the name of the sending node. So what is the name of the sending node here? The name of the sending node is C. So if you see here, the information, this is the information received from C. So why we have added only two columns? So in the previous discussion we discussed that only there is the receiving node only requires only first two columns, the last column is not necessary. So the information received from the node C is this one. See, the node C value is this one: A2, B4, C0, D infinity, E4. So here also A2, B4, C0, D infinity, E4. Okay, so these are the values received from the node C. Now what A has to do? A has to modify its routing table. What is the A's routing table? This one, right? So A has to modify its routing table and it has to modify its next column to the value of C, because it has received this information from the node C, right? So all the values now should be marked with C. Okay, so now the sending node will be the next node in the route. Okay, so for this particular A, the next node will be now the sending node, because it has sent all the information about the information related to all the connections for that particular node. Okay, now the third point. Now the receiving node compares each row of its old table. So if you see, this is the old table of the A. Now whenever C is sending its table, its information to A, now A's table will be updated, right? So now A's table has been updated, so this is the modified table. Now what node A is going to do? The receiving node means node A, it has to compare its each row with its old table. This is the old table, old routing table of node A. Now it compares each and every row of old table with the new table. Okay, so when it is comparing the old table with the new table, what happens? See, first row, this is the first row. Now it compares the first row of the old table with the first row of the new table. This is the old table and this is the new table. Now the first row will be compared. So after comparison, so the cost whichever is less. So here A 4, see, cost is 4, but here the cost is 0. Okay, so if the next node entry is different, okay, the next node entry is obviously different. Here it is C, here there is no next node information. So if the next node entry is different, now the receiving node chooses the row with the smaller cost. Okay, so what is the smaller cost among these two values? Obviously this one. So A will now update its new table, that is the modified table will be again converted to new table. That is, this will be the final table of A now after comparison. So A 0 and hyphen. Okay, next again compare the second row. This is 6, this is 5. So obviously 5. Okay, next the next row is 2. So when there is a tie, okay, so the next one is 2 and this is also 2. So when there is a tie, obviously it will keep the old one only. Okay, so the old value, that is C2 and hyphen. And again now if you see here D infinity and C, and here we have D3. So as 3 is the lowest value, we updated this to D3. 3 and hyphen. And finally, if you see here E6 and C, here E and infinity. Obviously, this will be the smallest value, right? So it is updated with E6 and C. So now if you observe, so finally, when it is comparing all these values, okay, so now the next node has been updated here to C. Now you have to compare, now you have to identify this value with this value. So now if you see, if you observe it clearly, what extra information does node A got from node C? The extra information that node A got from node C is that how it can reach to node E. So previously, if you see here, there is no information from at node A of how to reach to node E. That is the reason we have defined it with infinity. That is, it cannot reach. But now after sharing the information with node C, now the information at node A has been updated. That is, now A can reach to node E with the distance of 6 via node C. So this is the information now we in the sense the node A got from node C after comparison. Okay, so this is how actually we are going to update the routing tables. So there are many points we have to consider here. The first thing is that if we add any number to infinity, obviously the number will be still infinity. That is, if say there is some infinity distance, that is, if a particular node cannot reach to other network, and a node connected to the same node cannot also reach. That is, if you, this is A, okay, and this is C, and this is D. If C cannot reach to D with a particular distance, that is, if the distance is infinity, obviously if A to C is 2, then 2 plus infinity will be always infinity. This is what it is going to say. And the second thing is the modified table shows how to reach A from A via C. Okay, don't get confused about this point. If you see the modified table, this is the modified table, right? Again, I'm going to clear this. So actually this is the modified table, right? So what this modified table is going to tell us, if you observe here, from A to A it is 4. Okay, but actually initially original information about A. What is the original information of A? If you see here, from A to A is actually 0. A can reach to A with 0 cost because it is the node A. You cannot go from A to A with information 4. Okay. So what it is saying, now after modifying this particular value, what C is telling that A can reach to A via C. This cost is via C. Do remember, this cost is via C. That is, from A to C and C to A. If you see from A to C, what is the cost? From A to C is 2, and from C to A again 2. So 2 plus 2 will be 4. So this is how it is going to add. So that is the reason we need to compare this value with the old value. So what is the smallest value? Then we have to update that particular value in the final A's table. Okay. Now the third thing, so the only benefit this node A has received from the node C by sharing this particular routing table is that how it can reach the E. So previously node A do not know how to reach E. If you observe here, previously node A do not know how to reach E. But now after sharing the routing table with node C, now node A came to know that it can reach E with the help of node C with the distance of 6. Okay. So finally, each node can update its table by using the tables received from the other nodes. We know this one by this discussion. So in a short span of time, if there is no change in the network, that is, there is no failure in the link, or if the nodes are, if all the nodes reach a stable condition, then the contents of the tables remains the same. Okay, that is, if the network, okay, is in the stable condition, or if there is no failures, or if there are no problems in the network, then obviously the tables will be in a stable state and there will be no change. There will be only change only when there is a problem in the network, and sometimes periodically also the updates will be sent from one node to other node. Okay, we still have not completed the distance vector routing protocol. The other information, that is how it is being shared after sharing, how finally the algorithm works and all, we'll be discussing in the next class. Okay, thank you all of you.